Okay, in this next video, we're going to go ahead and do number 5. Number 5, I've given you the derivatives, so you don't have to worry about finding them. So here's one derivative, here's the next derivative. And so the goal here is to tell me where the intervals are increasing and the intervals are decreasing. So this is very similar to problem number 3 and number 4, especially part A. Whereas part B talks about concavity. And these two, the reason I put them together is the process is very similar. So let's start with part A. So most of you knew that what you were supposed to do is take e to the negative x squared, 1 minus 2x squared, and set it equal to 0. And then a lot of you did this. And then on the right, I think everybody was comfortable with adding 2x squared, dividing by 2, and then taking the square root. Some of you forgot that there's a plus or minus. Okay, here's a good place to maybe use the calculator because some of you struggle with picking the right points. So the square root of 1.2, I don't know off the top of my head, but this is equivalent to the square root of 2 over 2. I know the square root of 2 is about 1.4, so this is about, I think, point plus or minus 0.707. So that just helps me pick the right values. On the left, people struggle not knowing. Some people wrote x equals 0. That's not correct. But if you don't know how to do this, you could try taking the natural log of both sides. That's okay. And then you should use your calculator here. And your calculator should say not defined or error. And if that's the case, what that means is that this has no solution. So that's one way to get the right answer. The other way is to note that e to some power is never going to be 0. In fact, e to some power is always a positive number. If you understand the graph of e, this would be kind of, you would see it visually very easily. You know, the graph of e to the negative x squared looks like this, and it has an asymptote here, and it never touches that line. So if you knew the graph, and of course it would help you. But if you don't know the graph, that's why we have algebra. Algebra allows us to not worry about graphing so much, although graphing is very valuable, right? Since we're trying to find where it increases and decreases, and we're also trying to find local mins and local maxes, here's where you do the number line. So this is where this one's very similar to number 3. F prime, you have negative square root of 2 over 2. You have positive square root of 2 over 2. So a good point to pick would be 0, x equals 0. Another good point to pick is x equals -1 and x equals +1. The fact that it has symmetry is actually might be useful to some of you, but let's go ahead and compute this anyway. So we're going to plug this into the derivative. So f prime of -1 is equal to e to the -1 squared, 1 minus 2 to the -1 squared. Notice that this is e to the -1, which is positive. But here I get e1 minus 2, and this is now going to be -1 over e, which is obviously negative. So the function's decreasing here. So you can do that, or you can do this to show that the function's decreasing. If I plug in 0, I get e to the 0 times 1 minus 2 times 0, which is just going to be e to the 0 times 1, which is just 1, which is positive. And so, you know, on the number line, either a bunch of positives or one big positive, or some type of number chart. Again, I'll show you a different way that people do this in a bit. And then, of course, f prime of 1, e to the -1 squared, 1 minus 2 times 1. And we get e to the -1 times -1, or in other words, -1 over e. But the point is that it's negative. And so you have this. Now, the reason I like to use the number line is that I can see that, oh, sorry, I'm getting too excited here, it's decreasing. But the reason I like to see the number line is because here I can see that it's decreasing from negative infinity to negative radical 2 over 2. I can see that piece right here. I can see that it's decreasing from radical 2 over 2 to infinity. Notice that because I'm very neat, it's easy for me to see that. And then in between these two, from negative radical 2 over 2 to radical 2 over 2, I can see it's increasing. So now I just have to write a sentence because obviously you just can't leave it like this. I mean, we're supposed to write. And so the sentence should go something like this. What function are we dealing with? F, okay. F increases on the interval or intervals negative infinity to negative radical 2 over 2 and radical 2 over 2 to infinity. Nope, that's decreases. Sorry, let me change that to decreases. And increases, and F increases on negative radical 2 over 2 to radical 2 over 2. Okay. And then I'm going to go ahead and just answer the full question. Thus, F of negative radical 2 over 2, which is equal to something, is a local min, and F of radical 2 over 2 is a local max. If you're running out of time and you left it blank like I did, I would still give you full credit because I at least see that you're going to plug things in, and that's what matters, and that you know that the output is the local min and that the output is the local max and that you're using the chart. So that's enough. You are allowed to plug it in, of course. So if you plug it in, the first one becomes, or let me move this. I think I didn't leave myself enough room. But the first one is negative radical 2 over 2 to e to the negative 1/2. And the other one is radical 2 over 2 e to the negative 1/2. But you knew that we would have known that from symmetry. All right, that's part A. In part B, we want to do something similar using the second derivative here. So using the second derivative, can we determine the concavity of this function? And so to do that, and this video might be a long one, but to do this, we take that second derivative, f double prime of x, this is part B now. And we do 2x squared minus 3. And again, we set it equal to 0. So we definitely have 2x is equal to 0. We have e to the negative x squared is equal to 0. And we have 2x squared minus 3 is equal to 0. So here we get x equals 0. Here we get no solution like last time. And here we get x squared is equal to 3/2. So x is square root of 3 over 2. Okay. So square root of 3 over 2, again, I don't know that one off the top of my head. But it looks like it's the square root of 6 over 2. The square root of 6 is somewhere between 2 and 3. So this is probably between, this answer is somewhere between 2 and 3. If you have a calculator, go ahead, you can pause the video and figure it out. Otherwise, if you bear with me, I think I'm gonna go ahead and see if Desmos can take care of this for me. 1.2. Yep. Really? Oh yes, the square root of 6 is between 2 and 3. And if you divide by 2, yeah, that makes sense. Oops. Okay, anyways, 1.2. So now again, I create a number line and I have all these numbers. I just realized I made the same mistake a lot of you did. This answer is actually supposed to be plus or minus, plus or minus, plus or minus, plus or minus. So this is approximately plus or minus 1.2. So 3 critical points, there's 0, there's negative radical 3 over negative radical 3 over 2 and positive radical 3 over 2. And so a good number to pick here would be x equals 1 because this is about 1.2. So here x equals negative 1. Here maybe x equals 2 and here x equals negative 2. And then you plug those into the second derivative. And again, the goal isn't to compute these at this point. You kind of want to see if you can estimate these or do these really quickly. And so here, this part is negative. and this part is positive. And so this answer is actually going to be negative. For -1, this part is still negative, and this part is actually also negative. So that means this is positive. And of course, I should be filling out my number line. Negative, 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 positive, positive, positive. If I plug in 1, and sorry for the length of the video, but this might be a 15-minute one. So if you need to pause and take a break, feel free. Here, this part is positive, and this part is negative. And then finally, when you plug in 2, this part is positive, and this part is also positive. So of course, you can check all this with your calculators, but that should be positive. So here, negative, 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 positive, 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 positive. The question was to determine the intervals where it's concave down and it's concave up. So I'm going to use green for concave down. So it's concave down between negative infinity to negative radical 3/2, and between 0 to radical 3/2. And I'm going to use, let's say, red for concave up. So here, between negative radical 3/2 is supposed to be the whole thing. And 0, and here between radical 3/2 and infinity. And so to now just a quick sentence that says this, based on the chart, or based on my work, or however you want to say this, but based on chart, F is concave down on negative infinity to negative square root 3/2 and 0 to square root 3/2, and concave up on negative radical 3/2 to 0 and radical 3/2 to infinity. And that's, I mean, notice that procedure, this process is very similar to what we did in part A, except here there's no such thing as local min or local max, but you could talk about something called an inflection point, but I'm not asking you about those so far. Okay, last part is part C. In part C, you're supposed to use all this information to be able to create a graph. So my suggestion is that this part in part C is all pre-calculus. And so you should definitely look at the graph and see how these are all there. But the graph, I'm going to show you the graph in a minute. You can kind of see that the graph makes sense. So give me a minute here. All right, so to create the graph, I'm going to use a couple of things. So first of all, I have the mins, I have the maxes, I have the concavity. So I'm going to go ahead and put this all together into one nice graph. So the first thing, but one of the things I'm going to use is some of my givens. Okay, so one of the first things I see on part C is that it says that there is an intercept. So notice that there's an intercept at 0, 0, and that there's symmetry about the origin. So that's kind of nice because that means that here I know that there's a point on this side, but it also means that I should focus only on one side. Okay. So then the next thing I do look for the maximum, and the maximum, of course, is this. If you remember, the max. Oops, I went too far. The max happens right here at radical 2/2. And when you plugged it in, it's this number. That's okay. I don't really have to worry about what that number is. I just know that at radical 2/2, there is a max. Okay. And then I look at my concavity. It says it's concave up. So radical 3/2 is somewhere over here. maybe not that far away, but it says it's concave down from 0 to 3 radical 2. That makes sense because I expected this to go like this, but then it's concave up for the rest of the way. And so some of you were doing something like that, which makes sense, concave up. Then I have to go back and see that it says that it has a horizontal asymptote at y equals 0. Oh, and they're all real numbers, so I don't have to worry about any asymptotes at all. And so this asymptote means that it's concave up, but it doesn't go back up. It actually is concave up, but it goes down towards here. Okay. Now that I have this side, now I use the fact that it has symmetry about the origin. Since it has symmetry about the origin, that means that at negative radical 2 over 2, it also has a min, kind of like it does here. And then here at radical 3 over 2, that's where it's going to change concavity. So it's going to look something like this. And then because there's symmetry, it's just going to be the opposite of what we see over there. And so that's where it's at. And so if you labeled, local max, local min, and if this matched all the evidence that you have on part A and part B, then of course you would get full credit. And then the actual graph of the function so that you can see what it looks like is that one. So notice, not too bad. Very, very, very close. Not exactly, but pretty darn close. All right, again, sorry for the length of the video. These are long problems. Definitely do them step by step. Of course, if you've already done D1, then you might not have to do that one, but you may need it for parts B and C. So this one can help you get parts B and C if you do part A. I hope this helps.